Yeah, thank you so much, and thank you for organizing this event. I'm sorry that I missed both Monday and Tuesday, and I could only be here for my talk today. So Pasqal is a right. So Pasqal is a French company, originally out of the Institut Optique, but now it's a global company with offices in Canada and US throughout Europe, and also in Korea, with also communities in other countries as well. The company makes quantum computers based on neutral atoms. It should be a technology that you're all very well familiar with, much more than me. This is the roadmap of the company. The company plans to obviously make quantum computers commercially available with more qubits every day. Today, we have analog quantum computers available where you can globally address all the atoms trapped in an optical tweezer at the same time. Over time, new features will be added, like controlling each atom individually. This would be equivalent to applying arbitrary digital gates, as well as addressable two-qubit gates. So at that point, the device essentially becomes a digital quantum computer. So today you can consider it an analog computer, but one that can become a digital quantum computer. So currently we have commercially available hardware that is 100 qubits, but we have demonstrated 1,000 trapped atoms as well. There's a huge distinction between trapped atoms and qubits. So we can trap a lot of atoms, but to actually use them as qubits, it's a little more tricky. But in any case, it's on a roadmap to reach 1,000 qubits and then ultimately 10,000 qubits. Beyond that, we haven't made any concrete claims yet. Right. So this is the recent work we have done, and every time I say we, I mean many people except me. These are technologies that are available out of many labs. You should be familiar with Institut Optique, MIT, Harvard, Max Planck Institute. What Pasqal does really is to make these components at a commercial grade where they can be, sent to another lab and installed easily by a technician. So this is exactly what we have done with an optomechanical bench to produce almost 1,000 trapped atoms, more than 1,000 trapped atoms. And then also we've demonstrated rearrangement of about 800 of them. So neutral atom QPUs, we can currently do analog quantum computing with them. We can also do potentially digital quantum computing with them. I'm sure you don't need an introduction to analog quantum computing, but the idea is that we generally start from some ground state of Hamiltonian that is easy to achieve. So for example, in neutral atom case, it would be the ground state of all the trapped atoms. And then the parameters that we control are the continuous parameters of the Hamiltonian over time. And then at the end, we read out the output, and that's the result of our computation. The advantage of this technique is that it's basically the natural evolution of the system, and you have very few overheads. The issue is, and with fewer overhead comes high fidelity. The issue is that this is not suitable for universal quantum computing. With digital quantum computing, of course, you have control over each qubit and also each pairwise qubits. You can apply single and two qubit gates. You can do any sort of computation. We are far from achieving that and do useful things with it. So my pitch, which is actually my colleague's Konstantin's pitch, who has oversight on all these types of experiments we are doing, is that we want to use basically this natural evolution of the system, many-body quantum dynamics, to achieve quantum advantage. And quantum advantage is defined simply as being able to do something with the quantum processor that is very hard to do classically when compared to best known classical methods on a practical task. The practical task may be an argument of whether or not what we are choosing is actually practical, but time will show. So just a little bit about the technology in case you need a refresher. So we use optical tweezers to trap atoms. We then can do a fluorescence imaging to verify that these atoms are trapped. We can then do a rearrangement of the atoms. So for example, in this case, we have rearranged them to a square lattice. Originally, what you get is basically a binomial distribution of a trap that is twice as large, because each trap is filled with almost half probability. So you get something that is completely random. You have to rearrange them to get a structure that you want. We then address the effective two-level system by actually using two lasers. So we go from the ground state to an intermediate state, and then from the intermediate state to a highly excited state, Rydberg. The two important parameters of the lasers are the amplitude and the frequency, or the detuning from the transition. When we have Rydberg atoms close to each other, they interact and they exclude one another from transition. So you always end up with the blockade of one of the atoms, and you get this flip-flop between the two. So adding all of these together with some dynamics on how the amplitude and detuning are changed over time, you can get this, for example, structure here, which if you look very closely, every other trap is filled and every other is not. So some of them are excited to Rydberg states, and some of them are blockaded and are not converted. And then at the end, we turn on the traps, it pushes off the Rydberg atoms, and you end up measuring the ground states again. So you can see this one and the complement picture, and when you look at the distribution, these two have the highest occurrence. Okay, so continuing on using QPUs in its most natural mode, this is actually also what a lot of other teams are doing. I think the work that Barnes just mentioned, by kind of converting all the gates you have into actual pulses and kind of using the natural evolution of the system. It's a pattern that we are seeing a lot. Even this work by Google was ultimately able to achieve a higher entanglement that scales well with the size of the system by using this natural evolution of the system, or the analog mode of the hardware. There's also a similar work that our team has done on measuring the staggered magnetization of the neutral atoms. There's a very well agreement with the experiment and the numerical simulation using tensor network MPS. A computation that would take about 14 days at the time that this paper was done. Today, I would say that would be more like 1 day. Of course, the experiment itself is almost instantaneous if you forget about all the delays that you would actually face when you do the experiment. And if you wanted to repeat this experiment using gates, it would be equivalent to about 10 to the 6 gates with a very high fidelity, 10 to the minus 6. Right. So let me now talk about some of the applications we have in mind. The first one is amorphous solids, led by the team of Alexandre Dauphin. So crystals have high-order structure, long-range structure and order in them. So if you take the 10th or 20th nearest neighbor, there's order in that, and there are only specific values that you can observe in a solid. In an amorphous solid, however, you have the short-range order. So when you look at the first or second or third nearest neighbor, there's order in the system, but there's enough variation from one region to another that you don't see long-range order anymore. Amorphous materials have a lot of applications in insulators, semiconductors, and superconductors, and also quantum spin liquids. So what we have done, and again, by we I mean anyone except me, we've designed a method to generate amorphous materials by just kind of figuring out the coordinates that would resemble a amorphous material. So for example, if I refer you to the paper, there's an equation. Basically, we create systems with coordination numbers 3, 4, or even fractional coordination number. We make sure that no two atoms or no two locations are too close to each other. We also bound the maximum size of the system, and then we create enough variation in the location of the atoms to erase any long-range interaction, but to maintain short-range interaction. So these are kind of generated coordinates that you see that resembles this properties that we want: short-range order with no long range. And we consider antiferromagnetic Ising model, the system that we can as easily implement on our quantum computers. Then we look at, so in this work, we just look at simulated annealing of these systems. We are just preparing this and kind of studying these systems to ensure that, we are dealing with complex enough material that would later we do quantum simulations on. So if we look at glassiness and overlap, what we expect for square and Kagome lattice are the two plots you see. For square lattice, we have two peaks, and for Kagome, we have everything at the center. When we do the simulated annealing algorithm on these semi-disordered systems, we first look at the energy. So going from orange to blue, what we are doing is that we are increasing the number of sweeps in a simulated annealing algorithm. And here we have just sorted the energy of the best solution we find in each replica. So these are 60 replicas, I believe, yes. And ordered in energy, we clearly see that even at 10 to the 7 sweeps, we haven't reached convergence. So conclusion, these are hard enough systems classically, although that always depends on the choice of algorithm. The same is true about the Kagome lattice, and then when we look at the overlap, we clearly see deviation from ideal lattices. So the square lattice, for example, resembles, I didn't explain what the left panel and the right panels are. So the left panel are amorphous material we have created with the coordination 4 that resembles a square lattice. And on the right, we have again coordination 4, but one that resembles Kagome lattice. So locally, they look like a square lattice and Kagome lattice, but long range, they don't have any order in them. So the conclusion here is that these systems are hard classically, And even if you, just look at the quantum dynamics that these systems have, that would be even much more complicated. The idea is to move away from a system like this one here, where you have an ideal square lattice, even if experiments are faster than numerical simulations, we are dealing with a trivial system, so who cares? So the idea is to generate something more interesting. So the next use case that I wanted to talk about is quantum machine learning. The idea is that because of the nature of neutral atoms, that you can rearrange them, you can generate graphs easily, you can resemble graph structures using the position of the atoms. And machine learning on graphs have quite a lot of applications. So you can, for example, in a network of corporations, you can predict whether or not two organizations will partner. In a network of energy distribution, for example, you can do clustering and segmentation to, for example, optimize some sort of cost. In the network of people, you can detect communities for marketing purposes. Hopefully, we have a better use case than that. And yes, classification and regression on molecules for the purpose of drug discovery and prediction of properties of molecules. So these are just examples of why it would be interesting to do machine learning on graphs. So the most recent work we have done is based on graph transformers. The idea is that you take a graph, you have node and edge features, you augment these node and edge features with positional encoding of the graph, and this is usually done by Laplacian eigenvectors or random walk probabilities. And then you pass them to an ordinary transformer model. The whole idea is to get around the fact that you're dealing with graphs that don't have the same structure as simple feature vectors, numbers. So for quantum positional encoding, if we look at common classical ones, the ones I mentioned, then for quantum ones, the idea is to use correlations for positional encoding. And these correlations are very much similar to random walk, but they're quantum random walks. So here's an example of what is the motivation. So if we take a very contrived example of these two graphs, if we just look at the random walk, there's almost no distinction between these two graphs. But if we look at the quantum random walk or quantum correlations based on random walk, there's a huge distinction between the two graphs. And this is simply because that extra edge in the class 0 are closer, but in class 1 they're further away. And somehow this quantum random walk is able to detect that easily. And this is also what we see more in general. If you take this molecule that you can see here on the left, and we do different steps of random walk, what you get at the end of 4 steps of random walk looks pretty uniform, but when you do that with quantum random walk, it seems like it has detected some, there are some strong edges where, and there is no uniform distribution of these strong edges. So at the moment, this is where it is. On contrived data, there seems to be an advantage in using quantum random walk for the purpose of positional encoding. And the last use case is combinatorial optimization. You'll see that this is a very odd choice of topic, but I think it's very interesting to discuss all of this. So with neutral atoms, when we want to do optimization, it almost comes naturally if you've thought of maximum independence. If you have heard of maximum independence set, it's the type of optimization that we can do. The idea is that if you have a graph, maximum independence set would be the largest set of nodes that are mutually disconnected. We can only do unit disk graphs because connectivity of graphs is defined as the proximity of atoms, and there's a restriction on what type of graphs you can create. For example, if you have a star graph that has, let's say, 6 nodes attached to a center node, as you bring the 6 nodes closer and closer to the center node to connect them together, all the 6 nodes also become connected 2 by 2. So you can never create a star graph of degree 6. You end up with a star graph and a hexagonal around it. So here are a few examples of graphs that you can embed on a neutral atom system. This is a work done by AWS, and they've done these measurements, I believe, with the Q-era machine, which is the more or less the same technology, and then these blue boxes are done by CPlex. So CPlex can solve all these problems easily, and if you just take the top 2% hardest, the average time for the quantum hardware is higher, and also it seems to have a worse scaling than CPlex. The other thing is that these are all very easy problems, even up to the size of 2000, which now I realize these are just simulations, not actual hardware. These are still in the, even at the worst case, they're about 20 seconds. So not very hard problems. So we thought about generating hard problems. The only way we can, make problems harder, at least the two that you can immediately think about, are increasing the number of nodes and increasing the density of graphs. And in order to increase the density of graphs, you have two options: bring the atoms closer to each other. There's a limit to that. The other way is to reduce the amplitude of the laser. That will increase the blockade radius. But there's also a limit to that because at some point you don't have a laser to work with. And when the amplitude is low, the noise level becomes dominant. But let's just theoretically look at what it would look like. We looked at solving these problems. What we're reporting is the number of ticks, I believe, which you can translate to time. And think of red as hard problems and blue, yellow as relatively easy ones. What's achievable today is only that box at the bottom. So we are limited by 100 qubits. That will increase soon. But we are also limited by the density, how close we can bring these atoms to each other and how low we can go with the amplitude of the laser. So there's really a limit on how hard the problems can be. Another way of thinking about hardness is to look at the tree width of the instances we are working with. One interesting method is to get the edges and scramble them, and the more you scramble them, the more tree width you create, and these problems become harder. Let me skip to this one. Another idea for generating hard instances is to go to general MIS problems rather than unit disk MIS problems. So if you take, for example, this bipartite graph, you cannot embed it as a unit disk. One method is to use these techniques by this team to come up with this gigantic graph that faithfully translates the ground state of this graph to a unit disk one. So there is a way to take any graph and convert it to a unit disk graph. So, for example, the ground state is, you can see that three of them are red. That corresponds to the ground state of this problem, which is a bipartite graph. The bigger side is the solution. So now let's look at the unit disk MIS problems and MIS problems. They are in two different class of hardness. For unit disk MIS, we have polynomial time approximation, but for general MIS, we don't. So for general MIS, even estimating the problem is exponentially hard, exponential in the number of nodes, but for FITAS, for a given error rate, which things scale exponentially with error rate, the actual approximation is polynomial. So somehow we have converted a MIS problem to a unit disk MIS problem by only increasing the number of nodes polynomially. Of course, the problem is that in both cases, estimating, finding the ground state is still exponentially hard. But what happens is that by going from MIS to unit disk MIS, there's no guarantee that low-lying energies, the excited states, preserve the approximation. So even if you can approximate UDMIS in polynomial time, the solutions you will find for them are useless. They're all infeasible, and there are exponentially many of them. So by this transformation, even though you've preserved ground state, you can find a very high-quality solution like this, which is absolutely nonsense in the original problem. Remember that we had a bipartite graph and we wanted to find the independent set. But if you select all the nodes, that obviously is not an independent set. And there's no guarantee that you're just a small Hamming distance from best solutions. So any hope of correction would also be diminished. So this is why I said this is the interesting choice of use case, because it seems like achieving quantum advantage with optimization is very hard, if I don't want to say impossible. So that's exactly the conclusion we have right now for optimization. It's hard to achieve it's hard to see quantum advantage with the current knowledge we have. To generate hard instances, we have also, we looked at tree-width and the gadget method that is proposed for solving optimization problems seems to go nowhere. For amorphous material, we have high hopes. Right now, we are able to generate systems that are classically and quantumly very hard to study. We are in the process of obviously working on both numerical methods and experimental methods on these systems. And actually, for numerical methods, we are looking for collaborators to make sure that, whatever claim we make, someone can break it and we find something better. And for graph machine learning, currently, we are at the stage where with artificial data, we can see quantum advantage, at least in theory. This quantum advantage is limited to XY Hamiltonians. The case is not necessarily for Ising Hamiltonian, but this is still work in progress. And this is our team currently. Actually, I should say a fraction of our team. Just a few weeks ago in France, next to that boat, and we had a celebration for just gathering everyone together. And somewhere in the picture, I'm there as well. Thank you.
So I think this is just a clarification. For the three applications you talked about, they sounded like classical applications rather than quantum. Like we're not studying the quantum properties of amorphous material.
So for amorphous materials, yes, we are looking we are planning to look at the quantum dynamics.
I see.
The idea was to see if these systems are, they show enough glassiness and they're hard enough classically, and that is the case.
Okay, so then you would say quantum spin glass or quantum spin liquid. And then for the machine learning and optimization, those are both classical, right?
Yes.
Okay. So I guess, using a quantum computer for classical information problems sounds like tough.
Yes. So for optimization, the agreement is very strong. For machine learning, we are still investigating, but so the example that I showed is just a classical graph where quantum feature maps do better, but whether or not that holds with a more sophisticated classical algorithm is a different question. But I agree that is the possibility.
Thanks.
Are there any more questions? I do have one question. Have you tried any other combinatorial optimizations beyond, say, maxcut? Or
So basically, the same issue would exist because at the end of the day, you have to convert any optimization problem you have into the problem of maximum impedance set. That transformation will have, some sort of overhead, or one other issue that can happen is that arbitrary optimizations may not lend themselves to an MIS problem, so then mapping the Hamiltonian would not be straightforward. So for example, if you have an optimization where the coupling between two qubits is ferromagnetic, then you won't be able to map that easily, or at all, I would say.
Thanks. If there's no more question, let's thank the speaker again.